这个手机如果开高清录的话，它会有时间限制，就只录10分钟，然后这样的话就它不算很清楚，但是它能录时间非常长。
然后也能看得见。
反正我拿这个东西录是最模糊的。也可能上传的问题，它传上去就是一个加缩版。
probably already know that I just released your ED2 grade, and the median is 78. Okay, so anybody get higher than that, I think you can consider yourself pretty very good. Okay, and but if you are getting lower than let's say lower than 65, then probably we should. It's probably a good reason for us to have a small chat. Okay, any kind that you like, and. So if you, I will not automatically send back your test booklet, but if you want to look at it, come to my office. And I will give it back to you. Okay. So I just like to minimize the leak of the existing questions, because I might want to reuse it in the future if I'm going to teach this course again. Okay. So yeah. So any question about homework or midterm, anything? Logistic questions? No? Okay. Okay, cool. Yeah, so if you want to look at your midterm, and just click on this. Okay. So today my goal is to finish the chapter 5, which is the rest of the 5.4, and the most of it is going to be 5.5. So for 5.4, we have been talking about 3 different types of convergence, right? So more specifically, we have been focusing on the convergence, uniform convergence, and convergence, pointwise convergence, and the third one is the mean square or L2 convergence. We spend a lot of efforts to distinguish these 3 different things and to make it short. The uniform convergence is the strongest. It's the strongest already. And the pointwise convergence and the L2 convergence, they are both weaker than the uniform convergence, but it's hard to say which one is stronger, because you are going to see counterexample on both directions, which are a series of functions converge pointwise but not in L2 sense, and also a series of functions that converge in L2 sense but not pointwise. Okay. So this is the 2 and 3. It's hard to say which one is stronger. And we have been stating 3 different theorems about the Fourier how Fourier series will converge to a given function. Okay, and we have been stating these 3 different theorems without any proof. So today what we are first going to do is that we'll be first finishing the idea of convergence or the L2 convergence, and then we will demonstrate to detailed proof. Okay, but in the I should say in restricted cases. Okay, in more restricted cases, state a detailed proof for for the circumstances that the Fourier series converge pointwise or uniform. Okay. So we'll be first studying from the L2 convergence. Okay, which we have been talking about the L2 theory for the function. For a space of function for many times in this class. Which more specifically, we have a function space. Okay, which is, let's say, L2 and A and B, which means that we're talking about those functions that are we're talking about functions fx, okay, where x belongs to A and B, and the integration of, let's say, f squared x, okay, or probably it's better for me to use the absolute value to make everything to be okay. Absolute value of x squared dx from A to B. Okay, this guy is smaller than infinity, and this guy is also defined as the square of the L2 norm of fx. Okay, and we have been saying that the 2 norm, okay, the 2 norm is a way to measure how large is the function. When we are viewing the function as a vector, okay, vector has a length, right? So the L2 norm is also, you can also view it as the length, okay, so sort of length of the function in the L2 space. And therefore, since it is a length, and it is also defined as a metric, okay, to measure how different the two functions are, and therefore we are able to say that, okay, the difference. Let's say I'm having a function of f and also having a function of g. Then their difference, of course, is f and g. But since this function is generally not zero everywhere, then how do I measure how far it is from f to g in the space of the function? Then the result, our result is that, okay, well, we can use the 2 norm to measure the difference function between f and g. Okay, so f and g, again, the L2 norm of f and g, that can be defined as the square root of integration from a to b, f minus g, okay, fx minus gx, absolute value squared dx. Okay, the larger this value is, then we say under the L2 norm, the more different the f and g is. Okay, if f equals to g, more specific here, if f equals to g, that means that this guy is going to be 0. Which means that whatever will be integrated is going to be 0. Okay? Which means that the 2 norm of the distance is also 0. Okay, well, okay, so, but I should state it right away. Okay, I should state it right away. You see, this distance, and, or this norm, okay, it works in what case? It works in the sense of integration, right? So any difference that does not count in the integration will be ignored. Again, let me try to state again. F and G, okay, the 2 norm only measure the difference between F and G that could be accounted by integration. For any difference between F and G that cannot be accounted by integration, okay, then it cannot be measured. It will not be reflected by the 2 norm. Let me just give you one example right away. So let's say I'm talking about 2 functions. Let's say fx equals to 1, okay, for any x that's between 0 and 1. So far so good. And my gx, okay, equals to 1, okay. Let me put it this way. For any x between 0 and 1, and okay, x doesn't equal to 1/2, and equals to 0 for x equals to 1/2. Right. So that means that in this case, okay, this is my f, okay, and this is my g. This is my f. This is my g. Are they the same function? No, not the same function. Right? They are very obviously different from each other. But you see, the only difference place is what? Is that, okay, they are only different at one point. Okay, they are only different at one point. So that's good. So when we are doing f minus g, what we are going to get? We're going to have 0 almost everywhere, but except for what? Except for when x equals to 1/2. Right? For that function, what would it be its integration? Still 0. Which means that the 2 norm, in this case, the 2 norm between f and g, okay, the 2 norm between f and g is 0. Which means they are, although these 2 functions are completely 2 different functions, they are indistinguishable. Okay, they are indistinguishable in the L2 norm. Or we can say that, or another way to say it is that, okay, f and, or we can say that f equals to g, okay, almost everywhere. Okay, f equals to g almost everywhere. Does f equals to g? Well, we don't know, but f equals to g almost everywhere. So this is the difference. This is one example. Another example is that, okay, so then I can give you another example. So let's say hx, okay, hx the same. It equals to 1 for any x between rising between 0 and 1, and okay, x is irrational number. Equals to 0 for any x to be a rational number. Okay, so this is actually indeed a very bizarre function. First of all, is h a function? Is h a function? H is indeed a function because for every single choice of x, okay, it has a very clear and straightforward definition. It can only equals to 0 or 1. There's no ambiguity because any x, it is either rational or irrational. It cannot be either rational or irrational, right? So first of all, hx is indeed a function, and it equals to 1. Okay, it equals to 1 or whenever x is irrational, and it equals to 0 whenever x is rational. Okay, then the question is, if I would like to, so let's say if I would like to consider the integration of h between 0 and 1, what is that? Okay, and the answer is that, well, it will be impossible for us to integrate h using the Riemann integral. Okay, and it can only be integrated into the big sense. Okay, and since this is not a real analysis class, we're actually not diving into what does it mean by the Lebesgue integration for now. But the idea is that between 0 and 1, okay, the number of irrational numbers is much larger than the number of rational numbers. Okay, although there are infinite many rational numbers and also infinite many irrational numbers between 0 and 1, but compared to the irrational numbers, okay, the rational numbers are almost nothing. Okay, the rational numbers are almost nothing. Therefore, we can still say that although h only equals to 1 when x is an irrational number, we can still say that h equals to 1 almost everywhere. Okay, h equals to 1 almost everywhere. So again, I can say h equals to 1 almost everywhere, which is my f. Okay, which is my f, almost everywhere. And in this case, we also have that f minus h L2 norm. Okay, that is 0. Okay, but again, f and h, they are completely two different functions. One is continuous, completely uniform, everything is so regular, and h is, well, it's not even a continuous function. Actually, it has infinite many discontinuous points. It's actually discontinuous everywhere, right? Okay, my h is discontinuous everywhere, but indeed they have the same Lebesgue integral. Okay, and they are still almost the same everywhere. Okay, so and therefore, okay, with the idea of using the 2 norm to measure the difference between any two functions, then we could restate that the L2 convergence, okay, the L2 convergence of a Fourier series, okay, of a Fourier series, let's say an xn is, okay, is equivalent to that let's say first of all consider the 2 norm between f and the sum of the first n, okay, the sum of the first n Fourier terms. Okay, then the limit of this guy is 0 when n goes to infinity. Okay, and here one more thing is L2. So first of all, I first choose a big N, okay, and then I truncate the Fourier series for the first n terms. Okay, and of course this will become the sum of the first n term will become a function, and the difference between f and the first n term, okay, we can consider as L2, and the L2 convergence of the Fourier series to f, it indeed is equivalent to that when n goes to infinity. This L2, the L2 norm, okay, of the difference, it goes to 0. Okay, the L2 norm of this difference goes to 0. So consider these two ideas in mind. Okay, considering these two ideas in mind, well, we can deduce the next two theorems. Okay, we can deduce the next two theorems. Okay, the first, I would like to first state theorem number 6. Okay, theorem number 6, which is that, let's say, I'm having my fx and its Fourier series. Okay, it's Fourier series, which is indeed okay the sum of a and x n. Okay, and going from 1 to infinity. Okay. Well, the serial number 6 states that okay the Fourier series, okay, the Fourier series, let's say the sum n goes from 1 to infinity, a n x n, okay, it converges to fx in the L2 sense, okay, if and only if, okay, if and only if that the sum when n goes from 1 to infinity, okay, a n squared, and the integration of a to b x n x squared dx, this guy equals to, from a to b, fx squared dx. Okay, this seems to be a little bit complicated, but if you look into the interpretation of the left-hand side and right-hand side, actually it's very, very straightforward. So first of all, what is the right-hand side? What is the right-hand side? fx absolute a squared dx and equilibrium between a and b. What is that? Is that the two norm itself? It's the square of the two norm. Right? This is the square of the two norm. The right-hand side is what? The right-hand side is the square of two norm. Okay. What does it mean by the left? What does it mean by the left-hand side? Well, indeed, I'm having an an square in the, I'm having an an square outside, and I'm also having an integration of the square inside, right? But if I'm looking to every single term, okay, if I'm looking to every single term, then this is actually n from 1 to infinity. Okay, let's say the integration from a to b, because it's absolute value, I can just simply, a n x n x squared dx. Well, what is this? What is this? What is this integration? Let's not look at the summation at first. What is this integration?
It's the square of
This is the
square
of the two norm of what?
of one single.
A n x n, which is exactly the nth term in my Fourier series. So it's good? Okay. So this is actually the sum from n from 1 to infinity. This is what? This is actually, okay, the L2 norm, okay, the square of the L2 norm of every single term of my Fourier series. And this equation states that the left-hand side equals the right-hand side. Well, what does that remind you? The left-hand side is what? It's the sum of a bunch of squares. And the right-hand side is also a square. Okay. What theorem in geometry? That reminds you of what theorem in geometry? Pythagoras. The Pythagoras theorem, right? Okay. So simply like a squared plus b squared equals to c squared. This what happens when what? When my a and b, right? When my a and b are the two sides of an exact angle, okay, and c is the length of the third side. Okay, in this case we have a squared plus b squared equals c squared. So this is exactly what we know from the linear algebra, right? If I am using, so again, what is my xn? My xn is a orthogonal basis, right? My xn is a set of orthogonal bases, and the process that I'm using, the sum. Okay, I'm decomposing fx to the orthogonal basis will lead to what? Will lead to that. Okay, will lead to that actually. Okay. The square, okay, the square of this. So let's say I am having okay an arbitrary vector, okay, and I am decomposing that to any, okay, I'm decomposing that to any two sets of orthogonal basis, right? Right? And of course, then the true norm the true norm of this guy and the true norm of this guy, okay? Sorry, the square of the true norm of this guy, so a squared and b squared, okay? What about c squared? It's just that now the orthogonal basis, it has infinite many terms. So the sum goes to infinity. Sorry, the sum, I should put it this way. There are infinite many terms in the sum. But, okay, the sum of the squares are still finite. It should equals to the true norm, okay, of function f. Okay, so that's good. So this is called the Parseval inequality. This is called the equality Parseval. Okay, Parseval equality. And another very obvious stuff, which is related to this equality, is called the Parseval inequality. Which is that, you see, since the left-hand side has to sum to infinite many terms to be equal to the right-hand side, then if I truncate at any place, the left-hand side is going to be what? Can only be smaller or equals to the right-hand side, because every term in the left-hand side is positive. Or, every term in the left-hand side is non-zero. Sorry, non-negative. Every term in the left-hand side is non-negative, right? So this is called the Parseval equality. And we also have the Parseval inequality, okay? Which is that, okay, for any n that is not infinity, right? I'm having n going from 1 to n, my an squared, the integration from a to b, x n x squared dx. This is going to be smaller or equals to the right hand side, which is the true norm, the square of the true norm of fx. So that's good? Okay. But what's the difference here? The difference is that I'm only summing the first n terms. Here, I'm summing every term in the Fourier series. Okay. The Parseval inequality indicates that, okay, the sum of the square of the true norm of every term in the Fourier series, okay, is exactly the true norm, the square of the true norm of f. Therefore, if I'm only choosing a subset, okay, if I'm only summing from a subset of the terms, then of course it's going to be smaller because the square of the true norm is always going to be the square of true norm of anything is going to be non-negative. Okay, it's going to be non-negative. So that's okay. So this is the theorem 6 and theorem number 5. Okay, theorem number 5. For theorem number 5, this is called the least square approximation. Okay, then I'm first going to state the theorem and then going to give you a geometrical interpretation. Okay, so let's say again, let xn to be any orthogonal set of functions. Okay, and my f has a finite true norm. And n is fixed integer. Okay, and n is a fixed integer. Then, among all possible choices of constants, of n constants, from C1, C2, until Cn, the choice that minimize the true norm of f minus the sum from n from 1 to n, Cn, x xn, okay, is exactly c1 equals to a1, c2 equals to a2, and da 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 until cn equals to an. Here, the a's are Fourier series, are Fourier coefficients. Okay. The a's are the Fourier coefficients. And let me explain right away what does that mean. Okay, so now let's say I have a three-dimensional linear space. Okay, I have a three-dimensional space, and this is a three-dimensional vector. This is a three-dimensional vector. Now the question is that, okay, so this is my x, y, and z. The question is that which vector on the xy plane, could minimize its difference, or I should put it this way. I'm having a point over here. Okay? I'm having a point over here. Okay? Then the question is that which point on the xy plane, could minimize its distance between the red point? Which point on the xy plane could minimize its distance, okay, with the red point? Well, if you're asked to do that kind of question, what would you do? That's going to be what? That point is going to be what? That point is going to be the projection of the red point on the xy plane. Right? But how do you do the projection? How do you do the projection? Inner product, or more specifically, the Gram-Schmidt orthogonalization process, right? The Gram-Schmidt orthogonalization process. Which first we see, okay, so let's say this is a, so this vector, let's call it as the ax, okay, plus by, and then plus cz, okay. This vector is called, the red vector is ax plus by plus cz. Okay. Then for any vector on the xy plane, how do you represent that? How do you represent an arbitrary vector on the xy plane? It's going to be something like, let's say, okay, it's going to be something like c1x plus c2y, right? c1x plus c2y. So that's okay. Again, the question is, what choice of my c1 and c2 could minimize the difference? Then we call this guy should be my v, and this guy should be my w. What choice of c1 and c2 could minimize the distance between v and w? What choice could minimize that? What choice could minimize that? I mean, if I have my x and y and z to be orthogonal to each other, then also it's actually very straightforward, right? Then what is the choice of my c1 and c2?
A, B.
Just A and B, right? My c1. Only when my c1 equals to A and my c2 equals to B, then we're going to have it, right? Okay. But how do you obtain? But if you see before, you see here, by representing v into ax and by and cz, I am already using an orthogonal basis to represent, okay, this vector. Or more specifically, I am decomposing my v onto this basis x and y and z. So how to obtain? So the question becomes how to obtain the coefficient a and b and c. Right? How do I obtain the coefficient a and b and c? Considering that we already know that x and y and z are what? Are orthogonal to each other. How do I obtain my a and b and c? Just what?
Inner product.
Inner product. So my a should be exactly be what?
V dot V inner product with x.
Okay, my a should be the v inner product with x. Okay? And my b should be v inner product with y. So that's it? Okay. Wait a minute. Well, actually, you know what? Actually, there should be a normalization term because I didn't say that x and y are. I didn't say that x and y are normal, right? So actually, and then divided by the 2 norm of x, right? And then divided by the 2 norm of y. Okay, divided by the 2 norm of y. Because of what? Because you see here the same x. Okay, the same coordinate. Then the longer the y, the smaller the a. I'm fixing everything else. I'm fixing my v, I'm fixing my y and z, okay? And then if my unit x is becoming longer, then my a is becoming smaller, right? So it should be normalized. Okay, so that's basically speaking. That again, the choice of my c, of my coefficient c, okay, it would minimize the only chance for my choice from my C1 to Cn to minimize, okay, the L2 difference is going to be the case that C1 equals to the, yes, go ahead.
Yeah, for the branch mix, the coefficient should divide it by the square because we need to time y again after this coefficient.
Why is that? Why should I be split?
It is, for example, for a, we actually have a x, right? So we actually times the x.
No, I don't think that is true. So let's say I'm having something. Let's say 1, 1. Okay. Now my x equals to 1, 0, and my y equals to 0 and 1. Okay, so this is my b. And here I'm having
we cannot choose 1, 0.
1x plus 1y. Now let's say my x prime becomes what? My x prime becomes 1/2, 0. Okay, then what's my v? My v is going to become 2x prime plus 1y. Is that right? My v is going to become 2x prime plus 1y. And this is going to become my new a. This is going to become my new a. And it is, okay, and that is related to the norm of x, not square of the norm of x. So what's it? Okay? Again, you see, in this case, x goes from 1 to 1/2. Right? So I will be needing 2 pieces of x prime to represent that, which means that the coefficients, it scales up for 2, not 2 squared. Okay? Yeah. So, okay, so again, this is the, we can discuss that after this. Okay. So again, this is the form of the least square approximation, and again, we are having this form only because of that. The f is in an infinite dimensional linear space. Okay, f is in an infinite dimensional linear space. So the n, this n could be actually arbitrarily large. Okay, but how do we prove that? Well, let's say the proof. Okay, let's say the proof. Let's say my En is exactly the difference between f and for whatever choice that I have, n going from 1 to n, Cn, okay, x n squared. Okay, again, I am here. The Cn has not been. I haven't made my choice yet. I haven't made my choice for Cn yet. It's anything. It can be anything. So I'm just looking for. So now my goal is to make an appropriate choice of my Cn to minimize the En, right? To minimize the 2, this is the square of the 2 norm, okay? To minimize the En. Okay, and this, by definition, this is going to be from A to B, okay, fx minus the sum, okay, Cn, n from 1 to n, xn x squared dx, okay? And if I So this is a square containing n plus 1 terms. Okay, this is a square containing n plus 1 terms. And I am going to simply open the bracket. Okay, I'm simply going to open the bracket and see what do we have. Okay, and see what we have. If I open the bracket, then first of all, I'm going to have a term which is from A to B, fx squared dx. I'm just opening the bracket. I'm just trying to open the bracket. Okay? And then of course minus 2 sum. Okay, actually, you know what? Actually, let me say the sum for n from 1 to n to Cn, and then the integration A to B fx x n x dx. So this is the auxiliary term, right? And then plus for now we have already dealt with f squared itself and auxiliary terms between f and x. Okay, then the rest of it is going to be what? It's going to be the sum. Okay, it's going to be the square of the sum, right? And that can be represented as for any n from 1 to n and m from 1. And any m going from 1 to n. And Cn from A to B, xn, xn dx. Okay? But now we know what? Now we know that xn and xn, they are orthogonal to each other if n doesn't equal to n, right? Which means that their inner product is going to be 0. So in the same step, we are having n squared terms over here. But actually, how many terms do we only have? Only have n. We only have n terms, right? Because all other things are going to be 0 if I'm having my n doesn't equal to n, right? Okay. So this can be rewritten into, okay, so first of all, this is the true norm. The first term is the true norm, true norm of f, the square of true norm of f, and then minus 2, now the sum, okay, n going from 1 to n, Cn, this is actually the inner product between f and xn, right? And then plus the sum of n going from 1 to n, Cn squared xn L2 norm squared. Sounds good? Sounds good? Okay. And now let's complete the square, okay? Now let's complete the square. So now we are going to complete the square. We're now complete the square. What does it mean by complete the square? Well, you see, I would like to do what? I would like to, because you see, I would like to make a choice for my Cn, right? I would like to make a choice for my Cn. And you see here, if my Cn is the variable, okay, if my Cn is the variable, because Xn is something that has already been fixed. We have already made our choice of the orthogonal, of the set of orthogonal bases, right? So Xn is fixed. Therefore, and f is fixed. Therefore, the inner product between f and xn is also fixed. It's quite a bit. And also, my f is fixed. What can I change? What can I change in this formula? What can I change in this formula? I can only change Cn, right? And again, don't forget, the goal for me is to change Cn all the time, okay? To look for the minimum, to minimize, okay, the En, to minimize this guy, right? And therefore, okay. So why don't I just rewrite this equation to make it a little bit simpler? So let me say my f is something like a, okay, and the inner product between f and xn. Let's say it's something like, okay, bn, okay, and now the true norm, okay, the true norm of xn. Let's say this guy is actually something like wn, okay, wn squared. Wn squared. Then what we're really having, this guy is actually, first of all, sum from n to 1 to n, okay, So actually, Wn squared, Cn squared, okay, and then minus Q, Bn, Cn. I'm first writing down the last two terms, okay? And then plus and A. Sounds good? Sounds good? What kind of function is this? What kind of function is this? Wn is a fixed thing. It's a fixed. Wn is a constant. Bn is also a constant. An is a constant. Cn are something that we are changing. So what function is this? This is a n variable quadratic function, right? This is an n variable quadratic function. Okay. And the lucky thing is that because we have eliminated every auxiliary term between Cn and Cn in this step. Therefore, here you see Cn only has something to do with itself, right? Cn has nothing to do with Cn whenever my n doesn't use n, right? So if I would like to complete the square, then this actually equals to n from 1 to n, okay? So Wn Cn minus Bn over Wn squared. Okay? And of course, by doing that, by writing every bracket, by completing the square for every single bracket over here, actually I borrowed a square term which is called Bn squared over Wn squared. Right? So I have borrowed that and I have to pay for my debt. So which means that I need to do sum A and then minus the sum of n from 1 to n of a Bn over Wn squared. So that's good? So that's good? Everything still equals. Okay, now again, how do I mean it? Again, let's review what we have, right? Okay. Bn is something fixed. Wn is something fixed. An is something fixed. Bn fixed, Wn fixed, Wn fixed. The only thing we can change is the Cn. Again, how do I minimize this formula? When is this formula minimized?
Cn equals to Bn
Okay,
over W.
because you see here, everything are square, right?
Zero.
This formula is minimized if these square brackets are all what? All zero. Okay, are all zero. So to minimize En, again, don't forget this is my En, okay? To minimize En, I wish my Cn equals to Bn over Wn squared.
Yeah. So
My
this
Cn equals to Wn squared. Let's see.
It is square.
Oh, right, you're right. This is because over here, okay, I take it back. Yeah, you're right about this. This is because I am multiplying an x over here. Yeah, you're right. So here it actually should be squared. Yes, great catch. So, again, don't forget that my Wn, don't forget here, my Wn is essentially my xn squared, right? The true norm of the x, the square of the true norm of xn. And Bn is the inner product between f and n, so between f and xn. So this is essentially, okay, f xn over, okay, xn L2 norm squared, okay, which is exactly my an. Yeah, thank you, which is exactly my an. So far so good? Okay, so far so good. So again, to summarize what we have done, we have successfully proved that, okay, so for any set, so first of all, I have a function f in the L2 space, and I'm having an arbitrary set of orthogonal bases for this L2 functional space, which is xn. Okay. Now I am selecting arbitrary n terms from this set of orthogonal bases, and I would like to look into which linear combination of these n different orthogonal bases would minimize the L2 difference between f and the linear combination. Okay, and the answer is that exactly we would like to choose the Cn, okay, the coefficients exactly as the Fourier coefficients to minimize the L2 difference. Okay, to minimize the L2 difference. Okay, so let me just do one more example before we go to a break. Okay, so now this is example number 4. Okay, example number 4. And don't forget, what is the Fourier sine series for 1? Okay, sine series for 1. Okay, on 0 and pi. It is exactly 4 over n pi. Okay, sine n x. Okay, sum n going from n is odd. Okay, n is odd. Okay. Well, then what can you see? What can you say from the Parseval equality? What can you say from the Parseval equality? What can you say from the Parseval equality? Now, what is my f? 1 is my f. 1. What are my coefficients? Cn, 4 over n pi. These are my Cn. What are my xn? Xn are the sine x, right? Therefore, according to the Parseval equality, I'm having the integration between 0 and pi, 1 squared, dx. This guy should equals to the sum, n is odd. Here, 4 over n pi squared. 4 over n pi squared. And the integration from 0 to pi, sine squared nx dx. Okay? So that's good. Well, what is that? This is actually, then the left hand side, well, what is the left hand side? The left hand side is going to be pi. Okay, the left hand side is going to be pi. And the right hand side is going to be the sum, it's going to be the sum of n is odd, that 4 over n pi squared, and then pi over 2. Because we have already shown that, the true norm, right? The true norm of sine, or the true norm, or the square of the true norm of sine nx is always what? It's always pi over 2, right? We have calculated that one time in one of our previous lectures. Okay? So finally, by eliminating some pi on both sides, we actually obtain, the sum of n is odd, 1 over n squared. This guy actually equals to pi squared over 8. Pi squared over 8. And the left hand side is what? The left hand side is essentially 1 plus 1 over 3 squared plus 1 over 5 squared plus 1 over 7 squared, and then plus so on and so forth. So this is another equality. This is another equation. That's that could be useful to compute. What is pi? And in this case, it's actually pi squared. In this case, it's actually pi squared. Okay, so let's have a 5 minutes break, and then we're going to resume on 15.